title is Advantage and Opportunities with MEMS, the wafer level final test. The Michael is has the more than 25 years experience in the semiconductor industry. Currently, he has the position as the director of the sales and the marketing with the company name is Afore, a Finland-based the provider of the applications specific testing solution for MEMS and other semiconductor device. In this position, he has the high visibility on current and future the requirement for the testing application, and especially in about the final testing and also calibration of the MEMS sensor. So Mike has the technical background and also started his career as the service and application engineer for laser-based marking and the process equipment, and supporting first as Europe and then a global customer base. Before he working in the current company, he has several sales and marketing position for semiconductor equipment and related to the basically the wafer methodology, device handling and reliability. So today he will talk about the wafer the MEMS testing. So welcome, Michael gave the presentation. So let's start.
Today we're going to talk about some challenges that come with testing of MEMS devices in advanced packages. And we're going to explore some advantages and opportunities that come with it. First, we'll have a quick look into traditional MEMS packages and the test and packaging flow that is used for these devices. And after that, we'll have a look at advanced package types and the challenges and opportunities that come with them. Finally, we're looking into some solutions that are available in the marketplace today. Traditional MEMS devices are often packaged into SOICs, QFNs, LGAs, or metal caps, or depending on the application and the sensor type, also in some other SIM packages. Typical test flow for these devices, starting with wafer sort, starts with wafer sort, where the ASIC and the transducer is usually tested separately. Transducer testing at this level is typically strictly a electrical test that does not test the sensor performance itself. After wafer sort, both wafers go to dicing, and then the devices are packaged into a single package. This single package is then fully tested in final test, where each device is picked up with a pick and place handling operation from a tray, for example, to a test handler, and then in final test the device is calibrated by applying a stimulus in the test handler. Afterwards it is unloaded with pick and place operation, and then it is packaged for shipment, and this could be tape and reel, it could be bulk, or it could be JEDEC trays, depending on the type of wafer and the next processing step. For advanced package types, this is a bit different, and we're going to explore this for two different basic types of packages. So we're looking at the broad level for wafer level packages, where there is a huge variety, but we're looking at this from a broad level. And we're going to look into things like system in package and system on chip, which is a little bit different than wafer level packaging. Especially the test flow can be a lot different and can be optimized. That's why we look at it from a different perspective. Let's start with wafer level packages. With wafer level packages, the dies are often very small. They can be 1 by 1 millimeter, or they can be even smaller. And as a result, it's difficult to handle these packages once they are diced and separated from the wafer and the dicing tape. Also, mechanical alignment to the stimulus, especially for inertial sensors, is a challenge because of the short edges. It's very hard to align these devices mechanically. Then they have a low weight, which makes handling not easier because any small vibration can basically move these systems around. And they are fragile, which can cause mechanical stress to actually damage the device. On the other side, the ASIC is already joined with the sensor at wafer level, which gives you an opportunity to combine 3 separate test steps: just the ASIC testing, the simple electrical test that you usually do with the transducer at wafer level, and the final test and calibration into one process step. So how can this be done, or how to move forward from here, or with this type of package? Well, basically there are 2 options. One option is you can improve the current test flow, or within the current test flow you can improve the technology. But with this, the basic problems will remain. Because if you are able to handle a 1x1 millimeter device today, the next generation will be smaller and the handling issue will come back, for example. Or there is another approach. One can try to reduce the number of process steps that include handling operations, and thereby, and this requires a change to the existing process flow, but it also offers potential to streamline operations. So how can this be done? We'll start again with wafer sort, but this time wafer sort is not when the devices are separated. It's when ASIC and transducer is already combined together. So at this level, because the wafer is still complete, it's probably not a good idea to do the full calibration of the sensor, as some properties of the sensor might change after dicing. So therefore our proposal is to actually skip wafer sort altogether at this level and go to dicing, and from dicing basically go directly to final test at the wafer level. So the proposal would be to eliminate the pick and place operations that usually takes place for final test in final test handlers, and do the final test at the wafer level on the dicing frame. This requires a special system that does not only allow you to probe the wafer, but also apply stimulus. We will see that these systems are available in the market today. And because of the elimination of the handling process steps, the pick and place operations, they provide an advantage in yield. So after final test, the wafer can basically go to tape and reel if still needed, or it can be shipped directly on the dicing frame. What are the advantages? The advantages are I eliminate several device handling and process steps with this. And by doing this, I reduce risks and yield losses due to pick and place operations, for example. It also allows me to optimize my test sequences, as all components can be tested at once. So I can basically go from 3 separate process steps, testing steps, to one test where the entire device is tested and calibrated. And it reduces the number of operator tasks. And reducing the number of operator tasks basically also reduces the potential for error. Finally, I can get a reduction in floor space because there are a number of systems that are no longer needed. So, what's different when we look at system in package or system on chip? The fragility of the single components is still there, so that's basically the same, but I have one fundamental difference, and that's system cost versus sensor cost. If I go and put my sensor into a system device using microcontrollers and memories and potentially other things, then the cost for the sensor is relatively small. So putting a defective sensor into a system is actually a costly exercise because the cheap sensor kills the system device. So how do I go about this? I can go about this by optimizing the test flow depending on the component cost and complexity. How to move forward with this? If I do sensor test and calibration at system level, as I mentioned before, that's possible, but then I don't know if the sensor works before I put it into the system. So I have the risk of basically killing the system due to the cheap sensor. Or I can use a known good die approach for sensor testing. But this means that my sensor needs to be fully tested and calibrated before it goes into the system. And the best place to do this would be at the wafer level on the dicing frame, because this again avoids unnecessary device handling steps. And then what it also means is that potentially I need to add a short sensor verification to the system level test at the SoC or SiP level. How does this optimized test flow look like? Let me start from the right in this case with the system level test. So at system level test, only the entire system would be tested for system level functions. What this requires is that all the devices have been tested properly before they go into the system actually. Now, depending on the complexity of each device, the test flow for this specific device could be different. There could be devices where a full wafer sort is needed before dicing, and then there might be a need for final test afterwards, before the device actually goes into packaging. There might be devices where only wafer sort is needed before dicing, and then they can go directly into the package. Or in case of the MEMS sensor, our proposal would be to skip wafer sort, like we did with the other package types, with the wafer level package types, and go to dicing, and from dicing do the full sensor calibration at final test before it goes into packaging, and then moves on, and then the system moves on into system level test. And then from there, the entire package could go into tape and reel or any other form of shipment, basically. So what are the advantages of optimizing the process flow around test and packaging? It allows you to minimize the yield losses due to bad components at the system level. Basically, because you ensure that all the devices are tested properly before they go into the system. And it allows you to optimize your cost of test by minimizing the test steps where possible. Let's have a look at solutions that are available in the market space today. And let's start with probing of environmental sensors like vacuum sensors, pressure sensors, humidity sensors, or gas concentration sensors, or combinations thereof. For probing of these sensors and for calibrating them in real conditions, you need to put the wafer and the prober into a kind of environmental chamber that allows you to set and keep these conditions very precisely. The IOLOS system from Afore is a production-grade wafer probing station, a fully automated wafer probing station that allows you to set pressure levels, for example, with 1 Pascal accuracy, or gas concentrations in the lower ppm ranges. It can also be used to set humidity levels, and of course it comes with a temperature option. This system is available for wafer sizes up to 200 millimeter and perfectly suitable for typical wafer MEMS test applications today. For probing of motion sensors, you need, of course, a different approach because the stimulus is different for sensors like gyroscopes or accelerometers. For these kind of applications, Afore offers a system called the Chronos. The Chronos is a fully automated wafer probe station that allows you to either rotate gyroscopes continuously with yaw rates that exceed 720 degrees per second, or to set low G accelerometers into very defined positions towards Earth gravity for calibration. The system also comes with an optional magnetic stimulus, and with this it allows you to test full inertial sensor combinations at a 9 degree of freedom level. What are the conclusions we can draw from my talk in the past 15 minutes? I have provided an overview of a current MEMS final test handling strategies. And I talked about challenges that are introduced with advanced package types like wafer level packages or system on chip, for example. And then I have shown some improved MEMS test handling strategies that can help reduce the overall test cost for wafer level packages, for example, and increase the quality of calibration for these sensors when final test for wafer level packages is moved to the wafer level on the dicing frame. I have also talked about the possibility to replace a simple wafer sort test with a wafer level final test for system on chip type of devices, where the quality of the MEMS devices can be improved with this final test before these devices are put into the system on chip. And therefore the quality and the yield of the system on chip can be improved. So with this, I would like to thank you for listening, and looking forward to your questions.
I have two questions. First question is, you have been mentioned using the wafer after dicing and probing the device after dicing on the flame to replace final test. But how do you solve that problem about the tilt angle? Because after dicing, the chip already a little bit separate, although it's thick on the a flame. And then for example, magnetic test or gyro test is very sensitive for the angle or position angle tilt or position move. This is the first question. And second question is, if using this kinds of test method, how to solve the tri-temp test, high temperature, for example, up to 125 or 150 degrees C, and low temperature, for example, minus 40 degrees C for automotive application. Yeah, this is my question. And thank you.
Yeah, okay. So I'm going to start with the first one. What we have seen in past projects, applications, and existing installations today is that the level of misalignment that you get after dicing is actually can be neglected. What could be the bigger issue is actually the multi-site factor, because often when you do when you start probing after dicing, then the pad position actually moves a bit. So that's one thing that we noticed. That seems to be a limitation. But our systems, what we see currently with this is that we can achieve a multi-site factor in the range of 64. Right. So basically, we haven't seen an issue with the misalignment in existing applications. And to your second question, tri-temp testing. Extreme temperatures, minus 40 degrees or plus 150 degrees are an issue. The limitation there is the dicing tape. There are tapes available for a limited range. And most of our customers are actually not in the automotive space at the moment, not for wafer level testing. It's more in the consumer space.
Thank you.
Yeah. So, but yeah.
So you mean the flan is also the very key issue for wafer level test after dicing for automotive application, such wide range tri-temp test. Is that right?
Pardon, what type of test?
For example, a gyro or magnetic. Yeah.
So the other thing that we see with automotive is that most devices that we see in automotive are packaged after not in a wafer level package, but in other packages. And then customers typically prefer to do the final test in packages and not at the wafer level.
How about the magnetic sensor?
For magnetic sensors, we do have existing applications or existing installations already for wafer level testing. Not in tri-temp. Not in tri-temp. They are in ambient and hot.
Thank you very much. I have. Thank you.
Yeah, there's one question from audience here. The question is, if probe laser dicing, then tape and reel, is it also good way? Any risk? So basically the process is like the probe laser dicing, then tape and reel.
Can be done. This is a possibility. Most companies for MEMS prefer final test after dicing because they are afraid of changes to the sensor properties from the stress relief during dicing. So, but it is possible. And our systems can actually do both. So they can do they can probe on whole wafers before dicing and after dicing.
Okay. Thanks. I think the there's no more question here. Thanks, Mike, for your good presentation and also answer the questions.
I want to thank our sponsors once again, our premier sponsor, Test Tooling Solutions Group, JDT Technology, our honored sponsors, our distinguished sponsors, NIDIC, SV, TCL, Smiths Interconnect, TSC, and Feldman Engineering, and our media partners. If you go to the website, you can connect with them. And then, once again, very appreciative of Test Tooling Solutions Group and their support of TestConX China. Thank everybody again for your participation today. Please invite your colleagues to join us and certainly provide us any feedback you might have. So I thank you and wish everybody a good rest of your day. Thank you.